Okay, we talked about magnetism yesterday. I actually was going to put an article in here, but I forgot. It was like 4 a.m. About the magnetic changes of the Earth's magnetic, or the change of the Earth's magnetic field, that over the last 100 years has been reasonably dramatic. Now, this article, I think, was a little bit over the top in, the Earth's poles are going to shift and it's going to cause death to all. This article also said that it's been about 780,000 years since the Earth's magnetic poles switched, which differs from what I had read before, but new information comes all the time on these. It's not like anybody has record books that they kept for the magnetic field. What we're going to talk about today is the force on a moving charge when it's in a magnetic field. Last class period, I mentioned that if you have just a stationary charge in a magnetic field, there is no force. It has to be moving. And I, at the last moment, got to the equation that said the force on a charge in a magnetic field is force is equal to QV cross B. So this equation here is really important. The force acting on a moving charge in a magnetic field. So that has two pieces to it because it's a right-hand rule. Because it's a right-hand rule, we have both direction and magnitude that we need to figure out. So the magnitude is the easier part. Remember, a cross product means you're multiplying the perpendicular parts. So if I have a particle with its velocity like this in a region where the magnetic field is like this, then defining the angle theta as the angle between the magnetic field and the velocity, I can find how much of V is perpendicular to B or how much of B is perpendicular to V. So it's going to be the same calculation. You tell me, which one do you want to find? Which one do you want to take as my reference, V or B? Say it louder. B. I just realized the two sound so similar, B and V. So we're going to take B as the reference. So find the velocity component perpendicular to B is what I'm going to do. Because the cross product is multiplying the perpendicular parts. So that means I'm going to take my V vector and break it into two pieces. There's my right angle. It's pretty clear the perpendicular part is that part. And so if I have a right triangle, the hypotenuse is V, and angle theta between the hypotenuse and the adjacent side, how do I find the opposite side? This is something you've been doing all semester now, so it should come second nature. What trig function relates hypotenuse with opposite? Sine. And since sine of the angle is equal to opposite over hypotenuse, then the opposite is equal to hypotenuse times sine theta, so that'd be V sine theta. So there's my V perpendicular. And so the magnitude of the force is going to be the magnitude of the charge times V sine theta times magnitude of the magnetic field. And of course, I should, just to be consistent, put magnitude on the V as well. So that's how we find the magnitude of the force. So if it doesn't have a vector sign, it means magnitude. Q can be positive or negative. If I'm just looking for the force, I'm going to take the magnitude of Q as well, right? If I'm not looking at the vector. So the magnitude of the magnetic force is QVB, sine of the angle between the velocity and the magnetic field. Now for the direction, we use the right-hand rule. So I have a couple slides to remind us about the right-hand rule. You have at least one homework problem is doing the right-hand rule 3 different times. The right-hand rule is going to be used when you have a cross product. So here I have A cross B. Where else have we used a cross product in this class? Torque. Torque is equal to R cross F. So we've already seen the right-hand rule. We've already gone through this. The right-hand rule in general, A cross B, is going to have its direction determined by the directions of these two vectors. Now, there are two directions that with the cross product, the answer is always perpendicular to both of the two vectors. So if, for instance, I have two vectors that are both on my screen, so one is going like this, well, I'll just draw it. If I have two vectors that are on my screen, one's going like this, and one is going like this, there are two directions that are perpendicular to both of those lines. What are the two directions perpendicular to both lines? Out of the screen and into the screen. Those are the only two options that are perpendicular to both of the lines. So that means that my cross product direction is going to have to be one of those two because it has to be perpendicular to both of the vectors. So it's the product of the perpendicular parts of the vector, and its direction is perpendicular to both vectors. And then we have the choices of the left hand or the right hand, and science has decided we will use the right hand. And so we use the right hand. The right hand rule says that if you take your right hand and make your index finger in the direction of the first item in the cross product, and your middle finger in the direction of the second, and then keeping your thumb so it's perpendicular to both fingers, your thumb is the direction of the result. Now remember what I said first semester. Hyperextending your fingers, not allowed. You can't have, your index finger has to go straight, and then your middle finger has to bend toward the palm from your index finger. You can't have your middle finger bend back behind your index finger. It's not the way it works, okay? Can't do that. Have to do it like this. So sometimes we say, start with your fingers all pointed in the same direction, the direction of I, and then keeping your hand fixed, rotate your fingers toward your palm until they're parallel to the next one. That way you're going the right direction. Then your thumb points the direction of the answer. So going to my little picture here, if we're going to do A cross B, I'm going to take my right hand, point my fingers the direction of A. Then I need to rotate my fingers toward my palm to get to B. Well, I can't do it with the orientation of my hand right now. I'm going to have to rotate my hand. Now I can rotate my fingers toward B. And what direction is my thumb pointing? Into the screen. So the direction of A cross B is into the screen. Now what if instead of A cross B, I'd done B cross A? If I did B cross A, I have to start with my hand oriented this way. I have to make it so I can make my fingers bend in the direction of A. And what direction is my thumb pointing? Out. So B cross A is the opposite direction of A cross B. So it's really important that you get the direction straight or you'll go the wrong way. Hence this thing at the bottom, B cross A is minus A cross B. The directions are important. Here's pictures to illustrate what I just did, so you can come back and look at those since you can't see what I did on, the slides. Here's finding the perpendiculars that I already did. This is just showing that I could have found the perpendicular from B or the perpendicular from V, and I would have had the same outcome. Units. On Wednesday, I said the unit for magnetic field is the Tesla, and we would get to what a Tesla really was later. Well, now that we have our equation that says force is equal to QV cross B, or the force magnitude is equal to QVB, sine of the angle between them, now I can look at units. Because I have, for magnitudes, the magnitude of B is equal to the magnitude of force over QV sine theta. What's the unit of force? Newtons. What's the unit of charge? Units for velocity or speed. And sine is unitless. So that's my units. That's what a Tesla is. A Tesla is a Newton per Coulomb meter per second. Or we could say, well, a Coulomb per second is an ampere, and the ampere is actually the base unit. And so that's a Newton over an ampere times a meter. So now we can put more fundamental units to what the Tesla is, so we can say, this is how it relates. Nobody ever writes a Tesla as a Newton per ampere meter because it's kind of annoying. But it is good to know that there's a relationship here. Symbols that we have to become familiar and comfortable with. A circle with a dot means out of the page. Do you remember me talking about this first semester? I see a shaking of heads no. As it was explained to me, these are supposed to represent an arrow flying toward you. So you see the point of the arrow, that's the dot. So that means it's coming out toward you. These, the X or the circle with the X, I will always use the circle with the X, but you'll see it both ways, is supposed to be looking at the arrow flying away from you, so you see the fletchings. Now, of course, I think it's usually 3 rather than 4 on the arrow, but the fletchings, those little feathers to keep it flying straight, that's what the X is supposed to represent. So when you see those, they mean direction, and you need to be able to comfortably relate the direction to those symbols. Now, how to do problems. At this point, we have the equation for force. It's a little more complicated because the force now depends on the speed, and it depends on the direction of the speed, the velocity in other words. But here's our steps for solving forces using all the stuff we learned first semester after we've started with the force. So if the magnetic force will be 0 if the velocity is 0, the magnetic force will be 0. If the magnetic field is 0, it will be 0. And if the velocity is parallel to the magnetic field, you'll have 0 force. Any one of those 3 and you have 0 force. All 3 of those just come from that cross product equation. The force equals QVB sine theta for magnitude. So if Q is 0, it doesn't have Q as 0 as one of the options here. It has if they're perpendicular, so that's if theta is 9 degrees, if V is 0, and if B is 0. I guess it says for a charged particle, so right on a point charge. That's why it doesn't have Q as 0. So first, make sure that you have a magnetic force. If you have a magnetic force, then you want to find the velocity and magnetic field angle, the angle between the two, and find the magnitude of the force, determine the direction with the right-hand rule. Once you've found the magnitude and the direction, you're good to go. Always make sure you check the charge. If the charge is negative, that's going to reverse the direction. Right? Because it's not force is in the direction of V cross B. It's in the direction of QV cross B. So 3 questions, and then we'll do some samples. Question number 1. A positive charge travels east in a region where the magnetic field points down. Now I will draw a picture here while you're thinking this through. What direction is the force? So north, south, east, west. And so we have the positive charge travels east. So that's the direction of velocity. And the magnetic field points down. So the magnetic field is pointing down. Those are all circles with X's in them. Doesn't look a lot better. And the person I'm going to call on will simply lead us all through applying the right-hand rule to this. So I won't even ask them what their answer is. I'll just have them lead us through applying the right-hand rule. Okay, we're still waiting on 4 people. Well, north, south, east, west is in this plane, and so down is into the screen and up is out of the screen. James, Brandon, Michaela, Brandon and Angelina. You got an answer, Angelina? Okay. Okay. 0, 0, 1, 0, 1, 12, 6. Okay, Brittany, lead us through how we use the right-hand rule on this. Actually, why don't you come stand up here so people can see your hand in front of the screen. Okay, so okay, so she put her index finger in the direction of V because it's Q. V is the first one. Cross middle finger in the direction of B, and her thumb points north, and hence she got her answer. Perfect. Yes, just like. Okay, question number 2. A negative charge travels east in a region where the magnetic field points down. So once again, I'll draw a picture. Rebecca, James, Michaela, Nice, Jeff, Ashley, Brandon. Okay, everybody's answered. Okay, Michaela, it's easier for you. What was different between this problem and the last problem? The sign of the charge was the difference, right? Because the direction of the velocity was the same and the direction of the magnetic field was the same. So if you change the sign of the charge, what's that going to do to the direction of the force? It's going to flip it. So instead of being north, it turns out to be south. I forgot I didn't mark the correct answer here. Okay, now the last of our clicker questions. A positive charge travels east in a region where the magnetic field points east. What direction is the force on the charge? Of course, Brittany and Amanda. Okay. We had 17, 0, 3, and the rest were zeros. Okay, so let's go to Erika Villegas Perez.
Well, for this one, I was confused.
Uh-oh.
Yeah, because you know how the thumb and the place finger
Mhm.
went to the direction, but like how is that possible?
Mm-hmm.
So at first I was putting down, but then I feel like it's no first direction.
Anyone want to help her? Right, Brandon.
Isn't it where the velocity and the force where the B have to be perpendicular? They're in the same direction.
Okay, we're multiplying the perpendicular parts. So if there's no perpendicular parts, then it's got to be 0. All right, now let's do some work. Suppose a proton is moving straight down directly toward the equator. So here's a picture. Proton's moving directly toward the equator. First question. What is the direction of the force on the proton due to the Earth's magnetic field? So we have this picture. There's V, there's B. What's the direction of the force? Okay, somebody blurt out an answer when you're pretty confident. It's what way? Into the page. Okay, so we have into the page. Do we agree with her? We should, because she's right. Yes, Keela.
What does that mean in terms of this Earth is round? So,
Yeah, so this is looking, it's like a picture taken from the moon.
right.
And so we're looking at something that's coming in like this. It hits the Earth's magnetic field that's going to be deflected.
Okay.
And in this case, that would be deflected to the east. Now, how did she get that? I will, of course, go through the reasoning that most certainly Lauren went through. The force is equal to QV cross V. It's a proton, so Q is positive. No complications for direction. V is going toward the Earth. Orient my hand so my middle finger can point V and my thumb points into the screen, which was her answer. So now what's this proton going to do if it's got a force that's deflecting it to the east? it's going to veer away, right? So it's not going to hit the Earth. The Earth's magnetic field protects us from the cosmic wind, from the charged particles flying at us from the sun constantly, because it deflects them away, because those moving charges are going to have a force perpendicular to the velocity and perpendicular to the Earth's field. So there's a very important safety factor here in the Earth's magnetic field. So that's where the concerns come if the Earth's magnetic field goes to zero while it changes. We're not really concerned about the birds, I mean, we care about ecology, but we care a lot more about human lives, humanity. And the birds isn't going to harm us, but if we get a lot more charged particles hitting us, that's a lot more actual, real damaging radiation. So we got part A. Now part B. How does the Earth's magnetic field shield us from bombarding the cosmic rays? Well, I just said it deflects them away. Part C. Where on the Earth's surface is this shielding the least effective? Where? Okay, the top and the bottom, it actually is a stronger field because the lines are closer, but the direction, I mean, if you're parallel to the field, it's not going to make any difference at all. And if you come in at an angle not perpendicular, you know what's going to happen? It's only going to affect the motion that's perpendicular. And so what will happen if that charged particle comes flying in at an angle something like this? It's going to spiral around that magnetic field line. And then what's going to happen? If it spirals around the magnetic field line, the magnetic field lines come in at the north and south pole. What do we have? We're going to have charged particles come flying into the Earth's atmosphere closer to the poles. So this protection is not nearly so good if you're close to the poles. If you live in Alaska, if you live in Norway, you're getting more of this radiation coming at you because the Earth's magnetic field isn't deviating them away. Of course, it has some positive aspects. It's pretty, because this is what creates the aurora. The aurora occur when you have a large number of charged particles come into the atmosphere, interact with the gases, raising electron energy levels. Electron energy levels fall back down and give off the light. And so it's when you have a shower that's much more significant than normal of charged particles coming at the Earth that it gets bright enough for us to see. But it's going to happen much more at the northern and southern latitudes than it does closer to the equator, because you have the charged particles are going to be directed in toward the poles. So it's a very real relationship that we can see. And we like to see the northern lights. We don't like to think about, oh, look at the radiation we're receiving. Woohoo! Okay, let's do an actual put numbers into a problem type of problem. At a certain place on Earth, the Earth's magnetic field has a magnitude of 0.050 milliteslas. And it has a field direction that's 70% below horizontal. This here is called a dip compass. It's a compass that measures the angle at which the magnetic field is going into the Earth. Because the magnetic field is not parallel to the Earth. You can see it's dipped down quite a bit. Now, I don't think my dip compass is perfect, and there's lots of mags around here, so don't take that as the, straight from the mouth of God truth. But we have the field is directed 70 degrees below the horizontal, and its horizontal component points due north. So if I make a side view, here's up, here's north, and my magnetic field is 70 degrees below horizontal. And B is pointing that direction. So I've got my magnetic field described. Find the magnetic force on an oxygen ion. What's the charge of the oxygen ion? It's negative 1 electron charge. Moving due east at V equals 250 meters per second. I'll make it a vector. 250 meters per second east. North, not north. Okay, so we have all the information laid out here. We have to come up with a way to solve the problem, of course. So part A is just find the magnetic force. How will we find the magnitude and how will we find the direction? Okay, the direction with the right hand rule. So let's find the direction first. So taking my right hand rule, the magnetic field is like this. What direction, I didn't draw it, what direction is my velocity in this picture? The velocity is east. And so in this picture, east would be coming out toward me. So there's my velocity. So we have, let's start with V cross B. V is pointing out, so I have my fingers all pointing out of the screen. And then I orient my hand for B, so my middle finger is pointing the direction of B. And what direction is my thumb pointing? That's the direction of V cross B. How do I know it's 20 degrees? Because 70 plus 20 is 90. It's got to be a right angle. Now that's the direction of V cross B, but it did not ask what's the direction of V cross B. It asked what is the force. So how does the force relate to V cross B? Force is equal, what's the equation for the force? It's Q V cross B. So our equation is force equals QV cross B. And since Q is a negative value, my force is going to be like that. So my force is going to be 20 degrees below south. So Gila talked about the direction, so we found the direction first. How do we find the magnitude? Go ahead, Laura, you can say it. Yeah, we just plug in the variables. What's the angle between V and B here? It's 90 degrees. So they're perpendicular, which means when you multiply the perpendicular components of two perpendicular numbers, my magnitude is just going to be QVB. So the force magnitude is 1.602 times, oh, I don't have room to write it there. Not with writing that big. There's my Q. My V is 250. And my B is, well, let's just go 5.0. times 10 to the minus 5th Teslas. And so we need to calculate that. I'm sure this has an exponential. There it is. So did anybody else get an answer? That's the answer I got. Okay, it's the answer Gila got too. Thank you. So we have 2 times 10 to the minus 21 newtons at 20 degrees below south. Then it says compare the magnitude of the magnetic force with the ion's weight, 5.2 times 10 to the minus 25 newtons. Is that big or small compared to its weight? It's roughly 20,000 times bigger than its weight. Once again, the weight would be minuscule compared to this force. So we pretty much wouldn't worry about the weight. We would just worry about this force. But this says also to the electric force on it due to the Earth's fair weather electric field of 150 newtons per coulomb downward. So what's the force due to the electric field? What's the equation for the force due to the electric field? Definition of electric field is blank divided by blank. It's a very simple relationship. It's a force field. This reminds me, we have a test on Tuesday. This is going to be on the test, you know. It's the force divided by Q is the electric field. So that means the force is the electric field times Q. And look at that. 1.602 times 10 to the minus 19 times 150. That's going to be a lot bigger. That's 2.4 times 10 to the 17. So for this particle, the gravitational force is negligible compared to the magnetic force, but the magnetic force is negligible compared to the electric field force. Any questions about solving that problem? It was straightforward, but you have to remember your basic equations and how they fit. Now, as always, you'll have the equations on the test, but you have to know how they fit. You have to identify which equation applies here and how does it apply here. This here is leading into the next one. Let's just go to the next one. A charged particle moving perpendicular to a uniform magnetic field. Why perpendicular? Because that's the only component of its velocity that will have a force because of it. So you have a particle that's moving partially parallel and partially perpendicular to the magnetic field. It's going to stay at constant speed in the direction parallel to the magnetic field. And then what we find here is what we'll do in the direction perpendicular to the magnetic field. And what we have is a force that's going to be perpendicular to the magnetic field and perpendicular to the velocity. which means the force constantly changes direction as the particle changes direction. It's going to make it go in a circle because it'll always have a force that's tangential to the motion. So that means that it's going to do circles. Circles if V is perpendicular to B. Spirals if it's not perpendicular but has a perpendicular component. How do you find the radius? You say, well, the force tangential is going to be QVB, where that's the speed perpendicular to the magnetic field. And according to Newton's second law, sum of the forces is mass times acceleration. In this case, it's only changing direction, so that's going to be the centripetal acceleration of V squared over R. So we can say, the only force acting is the magnetic force. So Q V perpendicular B, I'm going to drop the perpendicular sign, is equal to M V squared over R. Well, let's solve that for the radius. And we see we'll have one velocity cancel, and the radius is mass times velocity over Q times B. So it's going to do circles with a very simple to calculate radius. Can you think of any way this could be useful to you? You as a budding scientist. Because we use it all the time in our science labs, mostly in chemistry labs, but I use it a lot in my physics PhD research. That's a good thought. It's not what's going on with the stir. It's that with the stir, you have a magnet, and then down below, you just have another electromagnet that's rotating. That's a good thought, though, because it's something going around a circle because of magnetism. That's how a mass spectrometer works. Now, there's different styles of mass spectrometer, but that's how your standard mass spec works. Your standard mass spectrometer has a source of ions, and then you go through an accelerating potential. Why do you go through that accelerating potential? To give them a known speed. So you start with the low speed, you accelerate them to a high speed. There is a little uncertainty in the speed based on you didn't know what the low speed was. But the bigger the high speed, the smaller we care about that uncertainty in the speed because it becomes negligible. So that first stage is speeding them up so we have a known speed. And then you put them in a magnetic field, and the radius is going to be mv over qb. We make the assumption that they're singly charged. And so if they're singly charged, then you have the Q is known, the B, that's an external field, so you know the B. And the speed, you know, the only thing left is the radius, tells you what the mass is. So what you do with this mass spec is you simply measure the radius. Now, of course, this is the diameter here. But you measure the radius and you determine the mass from that. So going through the math, we have radius is equal to mv over qb. Therefore, the mass is equal to radius qb over m, or over r. Oh, man. Mass over v. Now, we need to find the v. If we made it go through a potential difference of delta v, how fast is it going to be traveling? How can I find how fast it's going to be traveling after going through that potential difference? What's the name of the relation we start with? We did this a whole lot, like last Monday, or maybe it was Friday before. We're going to use the work energy relation The work net is changing kinetic energy. What's the work? Well, the work in this case is going to be the change of potential energy, the work done by the electric field, which is now, I wasn't careful about my signs. I just put Q delta V and didn't pay attention. You're going to have it. If it's a positive charge, then you're going to a lower voltage, and Q delta V is going to be negative. If it's a negative charge, you're going to a higher, it's going to be negative. So technically, there's a minus sign there, but I'm just going to focus on the magnitude. And so kinetic energy is 1/2 mv squared. In the approximation that the initial speed was approximately 0, then I have a simple relation that says v squared is equal to 2q delta v over m. And so putting that into this equation, uh-oh, now I have m two places, don't I? Got a little more work to do. So I'm going to multiply both sides by square root m, or actually that's divide both sides by square root m. Square both sides. And I have m is equal to r squared q b squared over 2 delta v. So there, hopefully I made no mistakes. We have the equation for the radius, or for the mass, based on the radius and the voltage I accelerated it through, the magnetic field, and the charge. So you can see that the charge is an important factor. If it's doubly charged, it's going to appear to have twice the mass. Or twice the mass? Doubly charged will appear to have half the mass. So I didn't think about that clearly still, but the mass, the charge makes a difference. We assume uniform or singly charged, but it may not be. That's a simple mass spectrometer. It's well, the kind I used was a quadrupole mass spectrometer, used a much more complicated system. But if you use something that's called an RGB residual gas, or RGA residual gas analyzer, that's what it uses. This here is going back to the first equation we had, that radius is equal to mv over qb. If a mass spectrometer has a beam of both lithium 6+ and lithium 7+, how much is the radius going to differ if they have the same speed? Well, we would just say radius of 6 is 6 mass proton v over qb. And radius of 7 is equal to 7 mass of a proton v over qb. And so the ratio of the radii is, of course, going to be 6 to 7. So it's a very quick and simple solution to see how the radius is going to change. Now, I did this quickly. Why did I put 6 mass of a proton here? Yeah, that 6 means it has 6 protons plus neutrons total. Well, lithium has 3 protons, so the 6 is 3 protons plus 3 neutrons. And 7 is actually 3 protons plus 4 neutrons. But the mass of a proton and the mass of a neutron are close enough that for friends like us, we'll treat them as having the same mass. Okay, we're out of time. Have a great Sabbath. and I'll see you on Monday, and then we'll have a test on Tuesday.